Okay, so today's video is going to be about classical physics. In classical physics, we will be talking about Stokes Law. Stokes Law. So, first of all, when we talk about Stokes Law, we will talk about two things. Let me make a. Okay, imagine this is fluid. Okay, fluid is not this color. Let me change the color, sorry. Oh, yeah. Let's suppose this is a fluid. Because Stokes law is regarding fluid from gas to it is also near gas, but the most is fluid. Fluid. Okay. In this, if we have a sphere, this is what we call this. This is a sphere, and we put the sphere inside this fluid. The force that fluid will experience will depend on several factors. F, that force will depend on something known as the inner property of this fluid, which will be of every fluid. It's called this symbol, which is known as viscosity, plus the radius or the distance of this object or the sphere, r. This is what the radius is, r, and the speed at which it's moving at, the velocity. Okay, and scientists, when they did scientist the experiment shows that it's equal 6 pi. It's an experimental figure. Experimental figure. So let me add it into equation, 6 pi. So this equation tells us how an object will experience force depending on the several factors which involve the liquids factor plus as well as the velocity and radius of the object. Okay, now uh, okay, let's that we have something known as weight is equals to drag force plus viscous force. Drag force is so that is as well as drag force and up thrust. They both can be known as same thing. So for me, I will just use up thrust. W equal up thrust plus viscous force. Now, when we talk about this weight, this weight is of the sphere. Let me write the following. Weight S is for sphere. Weight viscous force is for fluid. Okay. So, alright. Before talking about this, it's a complex one. Let's talk about this force figure as first. Okay. In this, what we'll talk about is uh, that if we have wait, no, if we have this sphere and this sphere. Oh wait, let me just make a difference which is clear. So the difference, which force or which sphere will move fast through this liquid, will be, we all know, this bigger one, because we know from the equation, over here, that the force will be more on the object which has more radius, and we can clear this, can make it clear by deriving, yes, we will be deriving one more, deriving the velocity of the sphere. Okay, and this will be over here, done over here. Or you know what, next page, because I need full page for it. Next page. Here we have deriving the velocity of the deriving the velocity of the sphere, or any sphere at which it's moving. Okay, let's get started. First of all, we'll be taking this equation over here, W equal D, or wait, I will be using U plus V. So first of all, WS means weight of sphere. We all know that weight of sphere is mg, where m is the mass and g is the gravitational force. Now we can expand this m into its factor. M is equals to density of the sphere plus the volume it covers. Now expand it again. Density of the sphere and volume g. We can expand it more. Expand this volume. We all know that the volume of a sphere is what? Nothing but 4 over 3 pi r cube, with pi r cube. Put that in this equation, we get Ws is equal to rho s 4 by 3 pi r cube g. Let me just rearrange it. Rho s. Now this is for weight. We just made the simplified version of weight. Not simplified, I mean the proper what we will be needing. It's not simplification, it's more complex. U is equals to, here the U upthrust will be the same. There will be no change in upthrust. It's just the viscous force. The viscous force is the U, or V, or 6 pi, sorry, pi I'm missing. 6 pi viscosity, and this is a symbol, Greek. It's a Greek symbol. Greek symbol or letter, and RV. Okay, then V is equals to, again, this V is of fluid, this is weight is of S, sphere. So fluid's viscous force is same as this, but there will be little change. 4 by 3 pi r cube g, but this density is of sphere, or liquid. It's just this will change. Otherwise, if I would have derived it in a simplified version like this, I would just be doing the same thing, so I didn't do it. Okay, now we have upthrust, we have weight, we have viscous force. We can put these all in this equation to get W equal U plus V. W is 4 by 3 pi r cube g, sphere, density of the sphere equal the upthrust, same as the force we have as usual, RV on the sphere. This is obtuse on the sphere, or the drag force on the sphere, plus the viscous force which is 4 by 3 r cube, oh sorry, 4 by 3 pi r cube g this. Let me take this whole thing into the next page because I'm not able to fit it here. Here, cube this plus. Okay, now let's simplify this to get our v, because that's what we want. V, velocity, is what we need. Velocity is what we need by, we will make velocity the subject. Velocity the subject. Okay. Now let's get started. 4 by 3 pi r. We are in our final stages. Always remember to differ between what we are talking about, because it will create similarities, because we have two equations of the same kind. The difference is that this is the density of sphere and this is the density of liquid. Now again simplified. Now pi's cancel each other, and r, if 4 by 3 4 by 3 r cube g this equal 6 rv 4 by 3 plus 4 by 3 r cube g g f of x, sorry, not f, this is this. It's not okay. When I move this whole thing to this side, I should get 6 sphere rv equal. Now take these as common, these and these, but we cannot take density of both common, because the density is different of both velocity. Density is different of both. And then what do we need is, not we have both, we have 4 by 3 r cube okay g okay, so 4 by 3 r cube g density of s minus sphere density of sphere minus density of liquid fluid, and here we have the other simplified version. Now one last task and we will make velocity the same. V is equals to r cancel, we'll cancel these r, so we get r cube, okay, 4 by 3 r square, or wait, we will not write 4 by 3 r square g of, let me write it then I'll explain, over, we have cancel this r, so r is gone. Now 6 to the power 6 and 4 by 3 is same as saying 2 over n, and here we have our simplified, or our equation for viscosity, speed of the object or the sphere, which is a sphere. We have a sphere. What will be its speed when it's going through that liquid? So if we study this equation, it says that a sphere with with a certain radius will be double times 2, and applying G, which is the gravitational field, and it's a gravi- yeah. So uh, yeah. So if I talk about the spheres again, this equation shows that the velocity of the object will be more on the bigger one, because the more the sphere's radius, the faster it will go down, depending because it will tackle more particles of the liquid. But when we talk about the smaller, it will be less, and it will tackle less particles in less time. So we talk about this equation. Thank you. Okay, let me write something. Why fast? Because the 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 sphere will tackle tackle more particles. Thank you. In more in less time. In less time. Thank you.